So section 17.8 has to do with investigating Q, the reaction quotient of solubility reactions. So unlike most equilibrium reactions, solvation can actually get stuck in a non-equilibrium state. And it can happen in a multitude of ways. So we're going to investigate three sort of different conditions. First, let's consider taking a very soluble salt like sodium chloride. So sodium chloride has a K, SP equal to 37.66. And let's suppose we take 0.5 moles of NaCl and we put that into 100 milliliters of water. What is going to be the reaction quotient? Well, we can find the concentration of Na plus ions. That's going to be 0.5 divided by the 0.1 liter, so that's 5 molar. And we can find the Cl minus concentration. That's also going to be 5 molar. And so Q, the reaction quotient, is going to be 5 times 5. That's going to equal 25. And Q is less than K. That means that this system is not at equilibrium. Now, ordinarily we say that when Q is less than K, the reaction is going to shift toward more products in order to establish equilibrium. Well, this reaction cannot shift toward more products. Why? Because we've run out of the reactant. The NaCl solid does not appear in the equilibrium expression, but it is still a part of the reaction. And if we run out of sodium chloride solid, then we can't shift to produce more products because there's just no reactant left. We can't make sodium ions and chloride ions appear out of nowhere. And so this describes a situation where the solution is unsaturated. And it's not at equilibrium, and that seems like to me at least, it makes me nervous. It makes me really want the system to reach equilibrium, but there's nothing we can do about it. There isn't enough sodium chloride left. And what this means is if we added any more sodium chloride, then it would readily consume that sodium chloride to shift to the right, at least until we reach equilibrium, if it's given the opportunity. But with only 0.5 moles of sodium chloride, it'll never happen. It'll be stuck in this non-equilibrium state forever. So that's an unsaturated solution. Well, now I'm forgetting the molar solubility of sodium chloride, but it's something like 6.5 moles. If you add exactly the right amount, and Q is equal to KSP, then that's what we call a saturated solution. And we actually already talked about this way back in like chapter 12. You can, I suppose, technically achieve a saturated solution by adding just the right amount of the solid. But in practice, the way we get saturated solutions is by adding an excess amount of the solid. So if I have a beaker here, and I add in some salt, and I stir it, and I give it some time, and there's still some salt that is left undissolved on the bottom, that tells me that the reaction has achieved equilibrium. It would dissolve more salt if it could, but once Q equals K, then the concentrations are going to remain constant from that point onward. And so a saturated solution is usually one that has some amount of the solid left undissolved at the bottom of the beaker. And I want to emphasize that that doesn't mean that stuff has stopped happening at the molecular level. We're dissolving things and then redepositing ions at equal rates. It's a dynamic equilibrium. You'll still have sodium ions and chloride ions coming off, but you'll also have new sodium ions and new chloride ions taking their place in a dynamic process. And one of the interesting things about the dynamism of this equilibrium is that the physical size of your crystals will shift over time. I wish I had it here, but I've got a vial that I've been keeping in my office for like the last 4 years that I've been here, where I put some sodium chloride into a little bottle and I sealed it up so that it's airtight. And I've just left it there. And the sodium chloride grains that I used to create this solution were very small grains like table salt. And if you could look at this vial today, you would see that it's got much larger crystal grains. And if I leave it for 20 years, we'll get some pretty substantial sized crystals, because in this dynamic equilibrium, ions are dissolving and redepositing, and they tend to dissolve on the smallest pieces of salt, and they tend to deposit onto the largest pieces of salt. And so the system over time grows larger and larger crystals. It's kind of a cool demo. I wish I had it with me here. And then finally, we can have situations where Q is greater than K. And we call these supersaturated. And there are kind of a couple of different routes that a supersaturated solution can go. So give me a sec here to get the slideshow set up. All right, so you may have seen a demo like this. I did it in my 1210 class. If I take something like lead nitrate, that's represented by what's in the test tube there, and the lead ions and the nitrate ions are soluble together, and so it's a colorless liquid. And you can take something like potassium iodide, represented here, where the potassium cations and the iodine anions are in solution, and that's a colorless liquid. Well, if you add them together, then the lead ions are able to find the iodide ions, and a new equilibrium expression comes into play. Ki2, potassium iodide, lead iodide, Pbi2, lead 2 iodide, is now in play. The lead ions can find the iodide ions, and if you look up their solubility product, it's very small. This is a sparingly soluble salt, and so if you were to sort of mathematically calculate Q, the reaction quotient, for the mixture of these two solutions, you would find that Q is much, much greater than K. That the solution is supersaturated. Well, in practice, those ions are going to immediately produce a new solid material, the lead iodide, and so the supersaturated state doesn't actually persist in the real world. It's just a mathematical signal to tell you, like, there's going to be the immediate and spontaneous generation of a solid precipitate. And that's a precipitation reaction. We've talked about those for years. Other times, you can actually, just because of the little nuances and quirks of these precipitation reactions, you can get a solution which is metastable in a supersaturated state. And so a good example of that is sodium acetate. If you heat up water, the solubility of acetate goes up. You can dissolve an incredible amount of sodium acetate into hot water. And then if you carefully cool it down, then even though Q is greater than K, it will remain as a solution until some sort of a shock or a catalyst begins the precipitation process. And it's only a metastable state. That means it's technically unstable. It just takes a long time for it to change. So it's once you begin the precipitation, that will cascade, and solid will be produced until equilibrium is finally established. But there is this window of time where it's metastable in a supersaturated state. Okay, and I've talked about that a couple of times before. There is a video in your textbook all the way back in like chapter 13, and you can find supersaturated acetate solution videos on YouTube because it's a really fun demo that a lot of people like to do. So just to review, we're going to jump over to one more figure here. If Q is equal to K, then the dissolution and deposition reprecipitation processes happen at equal rates, and you have a saturated solution with some amount of solid left undissolved. If Q is less than K, then your solid is still in the process of dissolving. You'll have ions leaving into solution at a fast rate, and your amount of solid will go down until you establish equilibrium. And if you have Q greater than K, then you've got more ions in solution than you need, and they'll be depositing and forming a new precipitate product through a precipitation reaction. Okay, that's all we need to know about that.